This is the fifth and final video on ideal gases in the A-level syllabus, and I'll be covering temperature and the kinetic theory of gases. We have covered almost all the objectives on this, so we just left with one, that is comparing PV is equal to 1/3 nmc squared with PV is equal to nkt, and deduce that the average translational kinetic energy of a molecule is 3/2 kT. Remember to subscribe to the Physics Tips for Cambridge Students YouTube channel and hit the bell notification so that you get alerted of future videos. Without much further ado, let's get started. Now, temperature and the kinetic theory of gases. Consider a volume of gas containing n molecules. The number of molecules per unit volume is small n, which is n/v. And the pressure of the gas, we have already deduced it as 1/3 n/v mc squared. Now, since we have said big N/v is equal to small n number per unit volume, so we're going to get 1/3 nmc squared like this, which previously we had PV is equal to 1/3 big N small m c squared. Also remember that I said you can substitute this, we can bring the volume down, and then we can have it as 1/3 rho c squared, where rho is the density. Now remember, c squared is the mean square speed of the molecules. For 1 mole of gas, the ideal gas equation PV is equal to RT, that's the equation of state. Making the kinetic theory consistent with the ideal gas equation, we are going to have it as 1/3 nmc squared is equal to RT. This n here, strictly speaking, should be the Avogadro number of particles. So this should be n subscript A. That's the one that is equal to that. We are assuming that the mean square speed of the molecule c squared is proportional to the temperature of the gas in kelvins in this case. If we are to take this one here further, we're going to get it as 1/3 mc squared is equal to R/NAT. And then this is going to give us 1/3 mc squared is equal to kT, where K is Boltzmann constant. Remember, Boltzmann constant said that it's equal to the molar gas constant divided by the Avogadro. So that's pretty much the same as what you're seeing there. The average kinetic energy of translation of random motion of molecules of a gas is half mc squared, so half mv squared is kinetic energy. So from this one, we are going to introduce a half. Since we've got a 1/3 there, we're going to multiply by 3 to cancel the 3, and then divide by 2 so that we introduce. So multiply by 3/2. If you do that, you're going to get half on this side here, and then on this side here, you're going to end up with 3/2 n/Avogadro. So that's going to be kT. So kinetic energy is equal to 3/2 kT. That's what we're having there. So that's been written here. So I've just deduced it from there. On my expression here, I just simply multiply by 3/2. So remember, I said if I multiply by 3, I'm cancelling out this 3. Then divide by 2, I am introducing a half. That will be effectively 3/2 kT. So the average kinetic energy of translation of molecules is proportional to the absolute temperature of the gas, is shown by that. Also, we can see that the mean square speed is directly proportional to the thermodynamic temperature T. So we can write PV is equal to nkt, that we started off with, as that. Variation of speed. The molar mass, remember I said molar mass is mass of 1 mole, so which means the number of particles will be Avogadro particles. So that will be Nm. So N is the molecules which have a mass of m. So if you say 1/3 m is just the same as saying nmc squared. So this is the molar mass, where this side here we've got 1 mole. So big M is the molar mass. Now, to get the root mean square speeds, remember I said it is the square root of the mean square speed. So on this side here, we've got the mean square speed times 1/3 m. So making the mean square speed the subject and finding the square root is going to be 3RT/m. So the square root of 3RT/m gives you the root mean square speed. So the root mean square speed is proportional to the square root of the temperature, yes, and also proportional to 1 over the square root of the molar mass. We're saying that the bigger the mass, the smaller is going to be the root mean square speed. So gases of higher molecular mass have smaller RMS speeds. So just to cement this, I'm going to show you an example. It says, show that if the mean speed of the molecules in an ideal gas is doubled, the thermodynamic temperature of the gas increases by a factor of 4. This should be the root mean square speed. Okay, so it says the mean speed and the temperature. That's what we have here. Right, so the temperature is proportional to the average speed squared. So if the speed doubles, then the temperature increases by a factor of 2 squared, which is equal to 4. Temperature is proportional to the average speed squared. So if the speed doubles, the temperature increases by a factor of 4 as well. Right, so moving on to the second example. Air consists of molecules of oxygen. The molar mass of oxygen is 32 grams per mole. Nitrogen, molar mass 28 grams per mole. Calculate the mean translational kinetic energy of these molecules in air at 20 degrees Celsius. Use your answer to calculate the root mean square speed of each of the molecules. So first of all, we are being asked to find the mean kinetic energy of the molecules. Then we are being asked to find the root mean square speed of oxygen and nitrogen. To get the mean translational kinetic energy, remember we said that the kinetic energy is 3 over 2 kT. So which is going to be equal to 3 times the molar gas constant times this temperature in kelvins. So we are going to convert the temperature 20 degrees Celsius to kelvins. So that's going to give you 293.15. Then we are going to divide by 2 times Avogadro constant, because we are going to consider 1 mole of that. So if you do that, the mean kinetic energy is going to be 6.1 times 10 to the power of minus 21 joules. The mean kinetic energy is equal to 3 over 2 kT. This is from this equation that we showed, this kinetic energy there being equal to 3 over 2 kT. We can simply use Boltzmann constant here in place of that. So 3 over 2 kT, which is just the same as saying 3RT over NA. So we could use Boltzmann constant here, which is 1.38 times 10 to the power of minus 13, and still get the same answer. So that will be 6.1 times 10 to the power of minus 21 joules. So the mean kinetic energy is half mc squared. Then we want to find c squared. M is the mass of one molecule. So one molecule is equal to molar mass over Avogadro. So the root mean square speed of oxygen molecule will be the square root of 2 times the mean kinetic energy over the M, which is going to be that times that over this is for oxygen, and then for nitrogen is going to be over 0.028. So that gives you 510 meters per second. Right, I'm going to end the video here, and please make sure that you subscribe to the Physics Tips for Cambridge Students YouTube channel. Signing out.